Section 2.2, Chapter 2, Modulus and Argument. Before we actually introduce what modulus and argument of a complex number are, let's talk about radians. Radians are just a different unit of angle unit, so measuring angles. So it stems from, if you imagine cutting out a sector from a circle that is 1 centimeter radius. Let's put centimeter, okay, and the part of the circumference is also of 1 centimeter length. So it's almost like an equilateral triangle, except you've got the curved part of the circumference arc here. This angle here that it inscribes is called 1 radians, so it's very close to 60 degrees. Now, if you remember that pi radians, you don't need to put that symbol when you write pi, is equivalent to 180 degrees, so 2 pi is going to be 360, and then you've got pi over 2, for example, that's 90 degrees. That's all you need to remember. To convert from degrees to radians, you need to times it by pi, divide by 180, and from radians to degrees, times by 180 divided by pi. Okay, so what is modulus and argument? So let's just plot a general point on an Argand diagram. It's going to be, let's call it P, and this has coordinates A and B. Our complex number Z is A plus IB. The modulus of that complex number is going to be notated in the modulus lines as modulus of Z. You can also use letter R, and this just means the length of this vector that joins the point, the origin to the point. So let's call it R. So you're going to square the real part, square the imaginary part, add them together and square root them, so apply the Pythagoras. Theta, which is called argument of Z, simply this is y coordinate, which is B, this is a x coordinate, which is A, so you will do arc tan B over A. Arc tan means tan inverse. There you go. So to describe this complex number with real part equal to A and imaginary part equal to B, you can also do that by giving me its modulus and argument. Okay, so we just as a convention, this angle here is measured clockwise, so positive direction is anti-clockwise, and measured clockwise would be negative direction, depending where your argument is between 0 and 2 pi, or between minus pi and pi. It's common to use throughout the book the argument from minus pi, which represents 180 degrees, and pi, and this is called, if the argument falls between those two values, it's called the principal argument. Okay, this is example 4. You've got a complex number 2 plus 7i, and we've got to find the modulus of that complex number and its argument. So modulus of Z is just quick Pythagoras, 2 squared plus 7 squared square rooted, so 4953 square rooted. And the argument, I always like to sketch it regardless of what I have. So it's going to be 2 across and 7 up. There's my complex number Z. So it's 7 here and 2 here. So arc tan 7/2. Make sure you are in radians, which is angle unit, so it's number 2. You want to be in radians. And we'll go to shift tan inverse of 7/2. 1.29 to 2 decimal places, and you put a radian symbol or write down radians. Okay, so you've got our answer here. Let's go on to example 5. This time we've got z equals -4 minus I. We've got to find the modulus. That's really quick. That's going to be just 4 squared plus 1 squared square rooted, so it's square root of 17. Now let's sketch this, the position of that complex number on an Argand diagram. So -4 across -1. So an argument needs to be measured from -pi up to pi. So we want to find out this angle. So in order to find this angle, I'm going to find this angle first. Let's call it alpha, and then subtract it from pi, which is equivalent to 180 degrees. So this is 1 and that's 4. So I'm going to do alpha is equal to tan inverse or arctan of 1/4. So we're going to do shift tan 1 divided by 4. That's 0.2449 radians, and then our argument of complex number z is going to be pi minus alpha. So let's do pi minus the previous answer, which is 2.89966. Since we want to go up to 1, I think it's 2 decimal places, not 1. 2.6, we'll change it to 0.90 radians. Okay, let's move on to exercise 2b. Okay, so next section is 2.3, a modulus argument form. So modulus, we know what modulus is, we know what argument is. So for this form, we're going to say r is equal to the modulus. We're going to use r, and then theta is going to be used for argument of z. So again, let's just very quickly draw a random complex number on a plane. This is going to be x plus iy. So that is horizontal distance is x, vertical distance is y. This is going to be theta, and the distance from the origin is r. So in order to find out what modulus argument form is, let's actually replace in our complex number x plus iy both x and y in terms of r and theta. So from this right angle triangle, you could see that x over r is equal to cos theta. That gives me x is equal to r cos theta. And then you've got y over r is equal to sine theta. So y is equal to r sine theta. Now if you put these two into our complex number, then you get r cos theta, add I r sine theta, and then you've got to factorize r in front of the bracket, and you'll be left with cos theta plus I sine theta in the brackets. So this form here is what's meant by modulus argument form. So if you're asked to express your complex number in modulus argument form, this is what you want to give as your final answer, with the plus in between the terms in the brackets. So let's plot our complex number. This is example 6, minus root 3 and I. So minus root 3 somewhere here. Let's put I here. And there is my complex number. So we need to find this angle, and we need to find the argument, which is the length of the vector. So first of all, let's just clarify how we can find theta. If we can find the angle that takes you up to pi and then subtract it, that will work perfectly. So this is 1, this is root 3. So alpha is going to be tan inverse of 1 over root 3. So this is a common one, pi over 6. So this is pi over 6 is 30 degrees. So my argument, which is theta, is going to be pi minus pi over 6. So pi minus alpha, which is 5 pi over 6. Modulus, which is r, is going to be root 3 squared at 1 squared square rooted. So this is the length of this hypotenuse. We're going to have 2. So argument, modulus argument form will look like this. Z equals to 2 cos 5 pi over 6 add I sine 5 pi over 6. Okay, moving on to example 7, you've got Z equals minus 1 minus I. Always sketch it. Minus and minus. We're talking about this complex number Z here. We want this angle here. So that's going to be theta is equal, I don't even need to do any trick. This is 45 degrees, this is 90, so it's 135 degrees, which is 3 pi over 4. Because we are measuring clockwise, so under the positive x-axis, it's given as a minus. R is 1 squared at 1 squared square rooted, so it's root 2. So Z is going to be root 2, and then you've got cos minus 3 pi over 4 at I sine minus 3 pi over 4. Now, if you give your answer like this, because cos theta, if you think about the cos graph, if I've got minus alpha here, that will give me the same answer as plus alpha. So cos alpha is the same as cos minus alpha. So you could actually write it like this. But then for sine minus alpha is going to be the same as sine alpha, but minus of that. So because it's an odd function, while cos is an even function. So you could actually replace it with minus sine 3 pi over 4. This is quite common to give your complex number like this, but if the question asks you to give you in argument, modulus argument form, then this is what needs to be given, the one with a plus, not the one with a minus. This is just an alternative way of writing the same answer. Okay, so 2C, example 2, example 7 leads you up to exercise 2C.